So imagine stepping outside on a really clear day, and you grab an apple, right? And you just throw it straight up into the air.
Right. A pretty standard human experience.
Exactly. I mean, your entire life, every single interaction you've ever had with the physical world has trained you for what happens next. The apple leaves your hand, gravity immediately starts pulling against it. It, slows down, reaches its peak, and falls back to the ground.
Yeah, that's just basic physics.
But now, imagine you throw that exact same apple, and halfway up, instead of slowing down, it suddenly accelerates.
Oh, wow.
Like it just shoots upward, moving faster and faster, completely ignoring the mass of the Earth, and rockets off into deep space.
I mean, that would completely shatter your foundational understanding of how reality operates. You'd probably assume your eyes were just, playing tricks on you.
Right. You'd think you were going crazy. But that exact sense of profound, reality-breaking confusion, that is exactly what swept through the global astrophysics community in 1998.
It was a massive shock.
Because the universe wasn't slowing down, it was accelerating. And the culprit behind this is something so pervasive and so mysterious that we are still, to this day, struggling to define it.
We really are.
So, welcome to a custom-tailored deep dive. We are taking a massive stack of sources today. I mean, we've got NASA briefings, the latest dark energy spectroscopic instrument results.
The DCI data, yeah. That's some cutting-edge stuff.
Tons of it. Plus, incredibly dense quantum physics papers, historical archives on Albert Einstein, and even some really new cutting-edge critiques of our standard cosmological model.
It's a lot of ground to cover.
It is. But the mission today is to distill all of this into a clear, ground-up understanding of this invisible force that is literally shaping the cosmos.
Yeah.
This is essentially a detective story on a cosmic scale where, honestly, 95% of the universe is missing from the crime scene. So, okay, let's unpack this.
Well, I think we have to start by setting the absolute scale of the crime scene.
Okay.
If you picture, the studio backdrop behind us just dissolving away, replaced by a sweeping dark void under a canopy of billions of galaxy clusters, that is the canvas we're working on.
Right. The big picture.
Exactly.
Yeah.
And understanding dark energy goes far beyond just cataloging what's out there in the dark.
Yeah.
The stakes are ultimate. The nature of this force dictates the final fate of the universe and everything inside it.
Everything.
Every star, every planet, every single atom. But before we can look at how the story ends, we have to establish what the universe is actually made of in this current moment.
Right. We need the cosmic recipe. And according to the standard model of cosmology, which is called the lambda cold dark matter model, or lambda CDM, that recipe is just completely lopsided.
It really is.
Normal matter, the baryonic matter that makes up you, me, the microphone right here, the sun, every star we can see in the night sky, all of that accounts for only about 4.9 to 5% of the universe's total mass energy budget.
Which is a remarkably humbling statistic, if you think about it.
5%.
Yeah. Everything humanity has ever studied, touched, or observed through a traditional telescope represents what is basically a tiny rounding error in the grand scheme of reality.
It's wild. So what's the rest?
Well, the rest is divided into two distinct components. You have dark matter, making up about 25 to 27%. And then you have the heavyweight champion, dark energy, which dominates at roughly 68 to 70%.
Okay, wait, I want to draw a very hard line right here. Because people hear dark matter and dark energy, and they naturally assume, that they're two sides of the same coin.
Right. They just share a marketing problem with the word dark.
Exactly.
Yeah, they share the word dark simply because they do not interact with light. I mean, they don't emit, reflect, or absorb electromagnetic radiation at all, but their behaviors are fundamentally entirely opposed.
Because dark matter pulls, right?
Yes, dark matter is an attractive force. It has mass, and therefore it exerts a gravitational pull. It's essentially the invisible scaffolding of the cosmos. Without dark matter, galaxies wouldn't have enough mass to hold themselves together.
They just fly apart.
Exactly. They'd spin apart like a merry-go-round, moving way too fast. Dark matter clumps, it gathers, it forms halos around galaxies.
While dark energy is doing the exact opposite.
Precisely. Dark energy is a pervasive, repulsive influence. It actively resists clumping. Instead of pulling matter together, it is stretching the underlying fabric of space-time itself, pushing the galaxy clusters apart.
So it's like we're baking a cosmic cake, right? And we only have the recipe for 5% of the ingredients, the flour and sugar, the normal matter.
Right.
The rest of the cake is totally invisible. 25% of it is super sticky, actively trying to pull the crumbs tightly together into clumps. But the remaining 70% is not only invisible, it is actively trying to push the kitchen walls apart while the cake is still in the oven.
That is a perfect analogy. And, the most confounding aspect of that 70% repulsive ingredient is how incredibly weak it is on a local level.
Really? I would think it'd be strong if it's pushing the universe apart.
You'd think so. But the sources point out that the density of dark energy in our local solar system is roughly 7 times 10 to the negative 30 grams per cubic centimeter.
Oh, wow. Let's ground that number because 10 to the negative 30 is really hard to visualize. That's, what, a decimal point followed by 29 zeros and a 7?
Yes.
What does that actually look like in physical space?
To put it in perspective, that is the equivalent energy mass of a few protons spread out inside a box the size of a cubic meter.
Just a few protons.
It is basically nothing. It's vastly weaker than the gravitational pull of the Earth, the Sun, or the Milky Way galaxy. If you hold your hands out right now, the dark energy passing through the space between your palms is so infinitesimally small, it cannot even be measured.
Wait, then how can something so incredibly weak dominate the universe? How does it make up 70% of everything if there's barely a trace of it in the room with me?
Because of the sheer volume of nothingness out there. Matter, even dark matter, is localized. It clumps into planets, stars, and galaxies. But between those galaxies are massive, unfathomably large voids of empty space. And dark energy is uniform. It is a property of the space itself. It's exactly as dense in the deepest intergalactic void as it is in the room with us right now. Because the universe is overwhelmingly composed of empty space, that unimaginably weak background energy adds up.
That makes total sense. When you sum the energy of all that empty space across the entire cosmos, it dwarfs the mass of all the localized clumped matter combined.
Exactly.
But since you can't, just put a telescope in your backyard and see an invisible, uniform background energy, how did we ever figure out it was there? Especially if it's so weak locally.
The irony is that the astrophysics community stumbled upon it while trying to measure the exact opposite phenomenon.
Oh, really?
Yeah. We need to look back at the state of cosmology prior to 1998. Ever since Edwin Hubble's observations in the 1920s, the scientific community knew the universe was expanding outward from the Big Bang.
Right. And the natural assumption was that all the mass in the universe, all those billions of galaxies, were exerting a collective gravitational pull on each other, acting like brakes on that expansion.
Exactly. The goal was to measure the rate of deceleration. Cosmologists wanted to know how hard the universe was stepping on the brakes. So to do this, 2 competing teams formed in the late 1990s. The Supernova Cosmology Project, led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees.
Okay.
They needed a way to measure astronomical distances with extreme precision, which is incredibly difficult in a dark void, so they turned to something called a Type IS supernova.
Right. These are the famous standard candles. But let's actually explain why they are standard, because, a star exploding doesn't exactly sound like a precise measurement tool.
No, it doesn't. But it requires a very specific stellar arrangement. A Type ES supernova occurs in a binary system, where 2 stars are orbiting each other. One of these stars is a white dwarf, the incredibly dense, dead remnant of a star like our sun. This white dwarf has immense gravity, and it begins siphoning gas off its companion star.
Like stellar vampire pulling material onto its surface.
Yes, exactly like a stellar vampire. As it steals this mass, the white dwarf gets heavier and denser. Now, a white dwarf is held up against the crushing force of its own gravity by something called electron degeneracy pressure.
Which is a quantum mechanics thing, right?
Yes, it's a quantum mechanical rule that says electrons refuse to be squeezed into the exact same quantum state. But there's a hard mathematical limit to how much mass this pressure can support. It was calculated by the physicist Subrahmanyan Chandrasekhar, and it sits at approximately 1.4 times the mass of our sun.
The Chandrasekhar limit. Okay, so the white dwarf steals mass, getting closer and closer to that 1.4 limit. What happens the exact moment it crosses the line?
The electron degeneracy pressure fails. Gravity wins. The star begins to collapse inward instantly, which causes the internal temperature and pressure to spike massively.
And boom.
Boom. This ignites a runaway thermonuclear fusion of carbon and oxygen. The entire star is obliterated in a fraction of a second, releasing a flash of light so bright it can outshine an entire galaxy.
Wow. And because this runaway fusion always triggers at that exact same mass, 1.4 solar masses, the explosion yields roughly the same intrinsic luminosity every single time.
Precisely.
It's like knowing exactly how bright a 60-watt light bulb is.
Exactly. If you place a 60-watt light bulb at the end of your street, it will look dimmer than a 60-watt bulb sitting on your desk. The intrinsic brightness hasn't changed, only the apparent brightness. By measuring how dim the supernova appears from Earth, astronomers can calculate exactly how far away it is.
But distance is only half the puzzle, right?
Yeah.
If they wanted to know how the expansion of the universe was changing, they also needed to know how fast the supernova was moving away from us?
Yes. And for that, they looked at the redshift of the supernova's light.
Oh, right, the stretching of light.
Right. As space expands, it stretches the light waves traveling through it. A stretched light wave shifts toward the red end of the electromagnetic spectrum. The faster the object is receding, the more its light is stretched and the higher the redshift.
Okay, so by mapping the redshift against the distance derived from the apparent brightness, these two teams could basically track the expansion history of the cosmos.
They could. So they ran the numbers on these incredibly distant ancient supernovae, entirely expecting to see the expansion slowing down. But the data came back looking entirely wrong.
How so?
The distant supernovae were much dimmer than the models predicted.
Which means they were further away than they should have been.
Yes.
Because if gravity was slowing the universe down, the expansion would have been faster in the past and slower now, meaning the light from those supernovae should have reached us sooner. They should have been closer and brighter.
You've got it. The fact that they were dimmer and further away meant the expansion wasn't slowing. The universe was expanding faster today than it was in the past. It was accelerating.
Mind-blowing.
This is where Saul Perlmutter's analogy of throwing the apple into the air comes into play. The collective gravity of the universe was supposed to pull the apple back down. Instead, an unknown, invisible force was actively overpowering gravity on a cosmic scale, pushing the apple out into the void.
It completely broke our intuition about the fundamental laws of nature, and it won them the 2011 Nobel Prize in Physics, and obviously forced the term dark energy into the scientific lexicon.
It did.
But, as earth-shattering as this 1998 discovery was, the theoretical foundation for this repulsive force had actually been laid, 80 years earlier?
Yeah, we have to talk about Albert Einstein. In 1917, Einstein had just published his field equations for general relativity. And general relativity was an absolute masterpiece. It redefined gravity not as a pulling force, but as the warping of space-time by mass. Massive objects create curves in the fabric of space, and other objects simply follow those curves.
But Einstein's own math presented him with a massive philosophical problem, right?
A huge one. The equations dictated that a universe filled with matter was inherently unstable. Gravity is universally attractive. If you place a bunch of massive objects in a static space, their mutual gravity will cause them to pull together, and the universe will collapse in on itself.
Right.
The equations demanded that the universe must either be expanding or contracting. It could not just sit still.
But at the time, the absolute prevailing scientific consensus was that the universe was static. It was fixed, eternal, unchanging. So to make his brilliant new equations conform to the accepted reality of a static universe, Einstein introduced a mathematical fix.
He added a term to his equations known as the cosmological constant, denoted by the Greek letter lambda. This constant acted as a repulsive force, an inherent anti-gravity built into the fabric of space itself. Einstein set the value of lambda to perfectly, exactly balance out the inward pull of gravity, allowing his theoretical universe to remain suspended in a stable, static state.
It was basically just a mathematical prop.
Yeah.
But then, in 1929, Edwin Hubble pointed his telescope at Mount Wilson toward distant galaxies and realized they were heavily redshifted. They were moving away from us in every direction. The universe was expanding.
And Einstein was reportedly devastated. He dropped the cosmological constant, famously referring to it later as his biggest blunder. He realized that if he had just trusted his original pure equations, he could have predicted the expanding universe a full decade before Hubble observed it.
Oh man, he viewed it as a cowardly retreat from his own genius.
He really did.
But the irony here is absolutely spectacular. For decades, lambda was relegated to the dustbin of theoretical physics, just a historical curiosity. Then 1998 happens. The expansion is accelerating. Physicists are staring at the data, completely baffled, scrambling for a mechanism to explain a universe pushing itself apart.
And what do? They dusted off Einstein's blunder, plugged lambda back into the equations, and found that it was the precise mathematical tool needed to model dark energy. The cosmological constant was resurrected. Einstein's biggest mistake turned out to be the key to understanding 70% of the cosmos.
That's incredible. But this brings up a critical distinction, though. We are fortunate about lambda as a mathematical tool, right? Like
Yeah.
a variable on a chalkboard. But if it represents 70% of the universe, it has to have a physical reality. What is the actual physical mechanism causing empty space to push on itself?
Well, the standard interpretation attempts to answer this by bridging general relativity with the other great pillar of modern physics, quantum mechanics. Specifically, quantum field theory. In quantum mechanics, the vacuum of space is not a void of nothingness. True emptiness does not exist.
Wait, even if you pump out every single atom, every photon, and create a perfect vacuum, it's still doing something.
It is boiling. The vacuum is a bubbling soup of quantum fluctuations. According to the Heisenberg uncertainty principle, there is a fundamental limit to how precisely we can know certain pairs of properties, like energy and time. On subatomic scales, energy can spontaneously fluctuate.
How does that look in the vacuum?
It allows pairs of virtual particles and antiparticles to pop into existence out of the vacuum, borrow energy for a microscopic fraction of a second, and then collide and annihilate each other, returning the energy to the vacuum.
So space itself has a baseline hum of activity.
Yes, known as zero-point energy. And because of Einstein's other famous equation, E equals mc squared, energy and mass are equivalent. Therefore, this constant bubbling energy in the vacuum should exert a gravitational effect. In the context of general relativity, a constant vacuum energy exerts a negative pressure, which translates into a repulsive gravitational force.
Okay, that sounds incredibly elegant. I mean, you take the bubbling zero-point energy from quantum mechanics, plug it into the cosmological constant from general relativity, and boom, you've explained dark energy.
The concept is elegant, but the math is an absolute disaster.
Oh, no.
When theoretical physicists sit down and calculate the expected energy density of all these quantum fluctuations using the established rules of quantum field theory, they get a number. Then they look at the actual observed density of dark energy driving the universe, which we established earlier is incredibly weak, just a few protons worth of energy per cubic meter.
Let me guess, the numbers don't match.
To say they don't match is the understatement of the century. This discrepancy is known as the vacuum catastrophe. The theoretical calculation of vacuum energy is larger than the observed dark energy by up to 120 orders of magnitude.
Wait, 120 zeros. A factor of 10 followed by 120 zeros.
Yes.
That is a number so large the human brain physically cannot comprehend it. The sources provided this analogy, and it's brilliant. Think about every grain of sand on every beach and in every desert on Earth. That is roughly 10 to the power of 20 grains of sand, and we are off by a factor of 10 to the 120.
Yeah.
It isn't a rounding error.
It is widely considered the worst theoretical prediction in the history of physics. It indicates a foundational flaw in how we are attempting to merge quantum mechanics with gravity. The physicist Matt Strassler highlights the depth of this problem in our source materials. He explains that different quantum fields contribute differently to the vacuum energy. Boson fields, like those for photons or the Higgs boson, contribute positive vacuum energy. Fermion fields, like those for electrons and quarks, contribute negative vacuum energy.
Okay, so in theory, if you have the exact right mix of bosons and fermions, their positive and negative energies could cancel each other out, leaving behind that tiny sliver of dark energy we actually observe.
Mathematically possible, yes, but practically absurd. Strassler notes that such a perfect cancellation balancing positive and negative energies down to the 120th decimal place without overshooting it entirely requires an unnatural, unimaginable level of coincidence. This is known in physics as a fine-tuning problem. It heavily suggests we are missing a fundamental piece of the puzzle.
Are there any theories trying to explain how we got a number so wildly off? I saw one in the sources called the omnium vacuum.
Yes. The omnium vacuum is a highly speculative but fascinating attempt to resolve the catastrophe. It proposes that before the Big Bang, the universe existed in a primordial static state with a vastly higher vacuum energy density. The theorists calculate this primordial density using fundamental constants to be around 10 to the negative 27 kilograms per cubic meter.
Which is much closer to the quantum predictions, right?
Exactly.
So the math wasn't wrong, it was just calculating the state of the universe before the Big Bang.
That is the premise. The theory suggests that as the universe transitioned into the Big Bang and began to expand, part of this massive primordial vacuum energy condensed into the matter and dark matter we see today. The remaining portion evolved and diluted into the incredibly weak dark energy we currently observe. It provides a narrative bridge, suggesting our current vacuum is a diminished remnant of a highly energetic original state.
Wow, it's a fascinating idea, but it really highlights just how deep the theoretical crisis is. Because the math is failing us so spectacularly with that 120 order of magnitude gap, we can't just rely on chalkboards. We need physical measurements. We have to map the universe with unprecedented precision.
Right.
Now, we already discussed the supernovae standard candles. What are the other pillars? How do you measure something that is entirely invisible?
Well, cosmologists never rely on a single type of observation. They use independent methods that rely on entirely different physics. If they all point to the same conclusion, the confidence level skyrockets. The two major supporting pillars are cosmic microwave background, or CMB, and baryon acoustic oscillations, or BAO.
The cosmic microwave background. I know this is often called the baby picture of the universe.
It is the oldest light we can see. It's the residual thermal radiation left over from the Big Bang, captured by extremely sensitive satellites like WMAP and Planck. The CMB shows tiny, microscopic temperature fluctuations across the sky. These tiny hot and cold spots represent the original seed fluctuations of matter, the infinitesimally small, denser regions that would eventually exert enough gravity to pull in more matter and form the galaxy clusters we see today.
But how does looking at a baby picture from billions of years ago tell us about dark energy accelerating the universe today?
Because it provides the baseline. It tells us exactly what the initial conditions were, including the precise geometry and density of the early universe. By comparing the initial state seen in the CMB with the current state of the universe, we can calculate what must have happened in between. And to measure that in between, we use the baryon acoustic oscillations.
Okay, and a very deep step-by-step breakdown of baryon acoustic oscillations. The phrase sounds like an advanced engineering elective, and I really want to understand the actual physics happening here.
No problem.
Yeah.
Let's travel back to the epoch right before the CMB was emitted, roughly the first 379,000 years after the Big Bang. The universe was completely unrecognizable. It was a scorching, dense plasma. Protons, electrons, and photons were all mashed together in a chaotic soup. The universe was completely opaque because any light photon trying to move would instantly crash into an electron.
So it's just a dense, glowing fog.
Exactly. Inside this fog, a massive tug-of-war was occurring. On one side, gravity was trying to pull the matter, the baryons, meaning the protons and neutrons, inward into clumps. But as the matter compressed, it heated up the photons trapped inside.
And heat means pressure.
Intense pressure. The photons exerted massive radiation pressure, pushing outward against the gravity. This relentless pull of gravity and push of radiation pressure created literal sound waves. Spherical acoustic waves propagating outward through a primordial plasma at more than half the speed of light. These are the baryon acoustic oscillations, expanding ripples of matter and light.
Right, so think of tossing a handful of gravel into a perfectly still pond, right? You get dozens of expanding rings of water interfering with each other. The early universe was basically like a three-dimensional pond filled with countless expanding ripples of sound.
That is the perfect visualization. Now, the critical moment happens at year 379,000. As the universe expands, it cools. It finally reaches a temperature where the plasma state breaks down. The electrons slow down enough to be captured by the protons, forming the first neutral hydrogen atoms.
And suddenly the electrons aren't flying around freely, which means the photons are free to travel without hitting them.
The universe becomes transparent. The light breaks free. This is the exact light we see today as the cosmic microwave background. But more importantly for BAO, the moment the photons escape, the radiation pressure completely vanishes. The outward push stops instantly.
What happens to the sound waves?
Without the pressure driving them, they freeze dead in their tracks. The ripple of matter stops expanding outward. You are left with a dense central region where the initial clump was, surrounded by a spherical shell of matter where the wave stopped. Because we know the physics of that plasma perfectly, we know exactly the speed of sound in the early universe, and we know it traveled for exactly 379,000 years.
Which means you can calculate the exact physical radius of those frozen spheres.
Yes. Factoring in the expansion of the universe over the last 13.8 billion years, the radius of those frozen sound waves today is approximately 490 million light years.
Wait, so the universe has a massive 490 million light-year yardstick permanently stamped into its structure.
It does.
How do we actually see it?
By looking at massive 3D maps of the cosmos, like the Sloan Digital Sky Survey. When cosmologists run statistical analyses on the positions of millions of galaxies, they find a slight but undeniable overabundance of galaxies separated by exactly 490 million light years. It is the faint echo of those primordial ripples.
If we know the absolute physical size of this yardstick, 490 million light years, how does that prove dark energy is accelerating the universe?
By using geometry. If you know an object is exactly 10 feet wide and you look at it from a distance, its apparent angular size tells you exactly how far away it is. By measuring the angular size of these BAO spheres at different distances, meaning we're looking at them at different eras in cosmic history, we can map the expansion rate of the universe over time. And the BAO measurements independently confirm exactly what the supernovae showed. The expansion of the universe is accelerating.
So the exploding stars and the frozen sound waves agree. The acceleration is real. But this brings us back to the most vital question. What is the engine doing the pushing? If the cosmological constant is mathematically troubled by the vacuum catastrophe, are there other options?
Yes, the theoretical physics community generally categorizes the attempts to explain this engine into three leading models. The cosmological constant, which is lambda, quintessence, and modified gravity.
Let's break down the mechanics of each. The cosmological constant is the reigning champion of the standard lambda CDM model, right?
In this model, dark energy is an intrinsic, unchanging property of empty space. The crucial metric physicists use to define this is the equation of state parameter, denoted by the letter W.
Let's explain what W actually represents.
W is a ratio. It is the ratio of a cosmic fluid's pressure to its energy density. According to the first law of thermodynamics, as the universe expands, the energy density of a substance should drop. If you have a piston filled with gas, and you pull the piston out to expand the volume, the density of the gas drops and it cools down. Matter behaves this way. Radiation behaves this way.
But the cosmological constant doesn't.
Right. For a pure cosmological constant, W is exactly -1. This implies negative pressure. Negative pressure does negative work as space expands, creating more energy. The result is that as the universe creates more volume, the density of dark energy remains exactly the same. You get more space, you get proportionally more dark energy, driving the acceleration outward smoothly and relentlessly forever.
Okay, but then there's quintessence. Where does that name come from, and how is it different?
The name borrows from the ancient Greek concept of a fifth element, an ethereal substance filling the heavenly realm. In modern cosmology, quintessence proposes that dark energy is not a rigid constant built into the vacuum, but rather a dynamic, evolving scalar field permeating spacetime. Meaning it can change. Crucially, yes. In a quintessence model, the equation of state parameter W is not locked at -1. It could be a value between -1 and +1. It can change over billions of years, and it can even vary slightly across different regions of space. Some versions of this theory involve tracker fields.
Tracker fields, what does that mean?
It suggests the dark energy field mimics the dominant energy of the universe for most of cosmic history. During the early radiation-dominated era, the dark energy field scaled its density to follow the radiation. When matter took over, the field tracked the matter. But eventually, the field's dynamics caused it to freeze or shift, causing its repulsive nature to suddenly dominate and drive the recent acceleration. It attempts to explain why dark energy is taking over now, rather than billions of years ago.
Okay, so lambda is a constant, quintessence is a dynamic field. What is the third option? Modified gravity. This is the idea that the engine doesn't exist at all, right? We just misunderstood the rules of the car.
It is the most radical departure. Modified gravity theories propose that general relativity, despite being tested and proven to astonishing precision within our solar system, fundamentally breaks down when applied to the unfathomably large distances of the cosmic web.
But how do you modify Einstein?
There are several avenues. One mathematical approach is FR gravity, which essentially adds terms to the Einstein-Hilbert action, the fundamental equation from which general relativity is derived. It tweaks the way curvature responds to mass over vast distances. But a more visual concept comes from string theory, specifically brane world models.
Brain with a B, like membrane.
Correct. Imagine our entire three-dimensional universe is just a membrane, a 3D slice floating inside a higher dimensional bulk space. In these models, gravity is the only fundamental force not confined to our membrane. It can leak out into the higher dimensions. Over massive cosmic distances, so much gravity leaks out of our universe that the attractive force weakens faster than expected, creating the illusion that a repulsive dark energy is pushing galaxies apart.
Oh, wow. And there was a note in the sources about early dark energy too, right?
Yes, early dark energy is a related concept attempting to solve the Hubble tension, the troubling discrepancy between the expansion rate of the universe measured from the ancient CMB and the rate measured locally using supernovae. Early dark energy proposes a brief, intense burst of repulsive energy very early in the universe's history that altered the expansion rate and then faded away, leaving the standard dark energy to take over later.
The analogy I keep coming back to is a thermostat. The cosmological constant is a basic analog thermostat. It is set to one temperature, it never changes, it just runs. Quintessence is a smart thermostat. It reads the room, adjusts itself over billions of years, changing the temperature dynamically. And modified gravity is the realization that the house isn't even insulated the way we thought it was, and the laws of thermodynamics we are using to program the thermostat are just wrong.
That perfectly captures the distinction. For decades, the analog thermostat lambda CDM was the undisputed king of cosmology. The data fit W equals -1 beautifully. But science is an iterative process of increasing precision. We never stop measuring. And in the last few years, the most advanced instruments ever built are beginning to show microscopic but vital cracks in that rigid foundation.
Yeah, we have to talk about the new heavyweights in observational astronomy. The Dark Energy Survey, or DES, and the Dark Energy Spectroscopic Instrument, DES.
Let's examine the Dark Energy Survey first. This was a monumental international decade-long effort. The Nobel teams in 1998 used a few dozen supernovae. DES utilized an unprecedented sample of 1,499 type ES supernovae. To process that sheer volume of data, they had to employ advanced machine learning algorithms to classify and analyze the light curves across billions of light years.
So they are throwing immense computing power at an enormous data set to pin down the exact value of W. What number did they get?
They found a value for W of -0.80.
Wait, -0.80 is significantly far away from -1.
In the realm of precision cosmology, it is an earthquake. Now, scientific rigor requires us to mention that when the DES team combined their supernova data with the cosmic microwave background data from the Planck satellite, the statistical margin of error stretched just enough to still include -1.
Right.
So the cosmological constant is not entirely dead, but as the researchers themselves noted, it is tantalizingly not exactly -1 on its own.
And the DSI results seem to be corroborating that tension, too.
DI is taking a different approach. It is an instrument attached to a telescope in Arizona that can capture the light from 5,000 galaxies simultaneously. It is currently building the most detailed 3D map of the universe ever attempted, tracking the influence of dark energy over the last 11 billion years. And the early data releases from DSI are showing even stronger hints that the dark energy equation of state is not a flat line. It shows indications of evolving over time.
So let's assume for a moment that these hints hold up and WE is actually fluctuating. What does that do to the physics of the universe?
It invalidates the cosmological constant entirely. If the energy density changes, it cannot be a fundamental property of the vacuum in the way Einstein modeled it. It strongly supports quintessence. It implies that the engine driving the universe is a dynamic, living field that is capable of evolving, shifting, and perhaps one day changing its behavior completely.
That's huge. But if a shifting dark energy field sounds disruptive to the physics community, we need to look at a vastly more controversial theory that is currently making waves. Because there is research suggesting that the entire foundation of the 1998 Nobel-winning discovery is flawed from the ground up.
You are referring to the research coming out of Yonsei University, led by Professor Youngwook Lee and his team. This is a crucial piece of the puzzle, and it requires us to look very objectively at the fundamental assumptions of our measurements. The entirety of the 1998 discovery of an accelerating universe rests on the absolute reliability of type Ia supernovae as standard candles. The assumption is that because they explode at the Chandrasekhar limit of 1.4 solar masses, every explosion is intrinsically identical.
Right. A 60-watt bulb is a 60-watt bulb.
But the Yonsei team posed a critical question. What if the environment the star was born in changes how the bulb shines? They conducted an extensive analysis of the host galaxies where these supernovae occurred. They found a 5.5 sigma correlation, which in particle physics and astronomy is considered the gold standard for statistical significance, meaning there is less than a 1 in a million chance it is a fluke.
Okay.
And this correlation showed that the luminosity of a supernova is heavily correlated with the stellar population age of its host galaxy.
Walk me through the physics of that. Why would the age of the galaxy change the brightness of an exploding star?
It comes down to stellar evolution and something called metallicity. In astronomy, any element heavier than hydrogen and helium is considered a metal. The very first stars in the universe were almost pure hydrogen and helium. When they died and exploded, they seeded the surrounding gas clouds with heavier elements forged in their cores, carbon, oxygen, iron. The next generation of stars formed from those clouds, incorporating those metals.
So, an older stellar population stars born a long time ago has fewer heavy metals than a young star born recently in a galaxy that has been heavily seeded with metals.
Exactly. The Yonsei team's research suggests that the progenitor white dwarf's metallicity affects the dynamics of the supernova explosion. Even though they both hit the 1.4 solar mass limit, the young, metal-rich white dwarf explodes slightly differently, specifically slightly dimmer than the older, metal-poor white dwarf.
And here is the trap. Because light takes billions of years to reach us across the universe, looking far away means looking back in time.
Yes, when we look at incredibly distant supernovae, we are looking at the young universe. We are looking at a population of younger stars.
So we look at a distant supernova, we assume it's a perfect 60-watt bulb. It looks really dim, so we conclude it must have been pushed incredibly far away by an accelerating expansion. But the Yonsei team is saying it isn't a 60-watt bulb at all. It's a 50-watt bulb because it's a young, high metallicity star. It looks dim simply because it is dimmer, not because it's further away.
This is termed the progenitor age bias. The researchers argue that the current cosmological models do not properly account for this stellar age evolution. When the Yonsei team applies a rigorous calibration to the supernova data to correct for this age bias, they make a staggering claim. The statistical evidence for an accelerating universe completely vanishes.
Wait, it vanishes entirely? The acceleration just goes away?
In their corrected data models, yes. This concept is often referred to in the surrounding literature as the dead universe theory. If the acceleration vanishes, we revert back to the pre-1998 cosmological assumption. The universe is simply expanding from the initial thrust of the Big Bang, and the collective gravity of all the mass within it is slowly, steadily decelerating that expansion due to normal thermodynamic entropy.
I want to pause here to make sure we are presenting this impartially because we're just conveying the sources here. The standard lambda CDM model is not purely reliant on supernovae. As we thoroughly explored earlier, the baryon acoustic oscillations mapped by DSI and the cosmic microwave background data from Planck provide massive independent pillars of support for dark energy.
Very true.
The scientific consensus heavily favors an accelerating universe. But the scientific method demands that we question every assumption. If the progenitor age bias holds up to intense peer review, the biggest cosmological discovery of the century, the entire reason the term dark energy exists, could be an optical illusion caused by stellar aging.
It highlights why cosmology is such a dynamic and fiercely debated field. We are attempting to reverse engineer the mechanics of the cosmos, using faint specks of light captured billions of years after they were emitted. Whether dark energy is a rigid vacuum constant, a shifting, evolving quintessence field, or an illusion born of miscalibrated standard candles, finding the ultimate answer is not just an academic exercise, it dictates the final chapter of the universe.
Which brings us to the end game, the fate of everything. How do these different theories dictate the end of the universe?
The scenarios are dictated entirely by the equation of state parameter, Wi. Let's begin with the currently accepted standard model lambda CDM, where W is exactly -1. This leads to a scenario known as the Big Freeze, or heat death.
Break down the mechanics of the Big Freeze for me.
If dark energy is a constant, the expansion of space accelerates forever. As the voids between galaxies grow larger, they create more dark energy, which accelerates the expansion further. Eventually, the expansion velocity between galaxy clusters exceeds the speed of light.
Wait, I thought nothing could move faster than the speed of light.
Nothing can move through space faster than light. But space itself has no speed limit on how fast it can expand. Once the expansion outpaces light, the light from distant galaxies can never reach us. The observable universe shrinks. The night sky goes completely black. Within our isolated fading galaxy, stars will slowly burn through their nuclear fuel and die. The universe becomes a graveyard of black dwarfs, neutron stars, and black holes.
That sounds incredibly bleak.
It is. Eventually, over trillions of years, even the black holes will evaporate via Hawking radiation. The universe reaches maximum thermodynamic entropy. It is a vast, cold, infinitely expanding void approaching absolute zero where no work, life, or computation is physically possible.
A lonely, freezing fade to black. What happens if the dark energy survey is right and the equation of state is less than -1?
If W is less than -1, we enter the realm of phantom dark energy. This triggers a scenario called the Big Rip. In a big freeze, the repulsive force only pushes galaxy clusters apart. The gravity holding individual galaxies together is strong enough to resist it locally. But phantom dark energy is aggressive. Its density actually increases over time as the universe expands.
So the repulsion gets stronger on local levels.
Precisely. It becomes a runaway catastrophic feedback loop. First, the phantom energy overwhelms the gravity of galaxy clusters, tearing them apart. Then it overwhelms the gravity of individual galaxies, stripping stars away from the core. Fast forward, and the repulsive force in our local space becomes stronger than the gravity holding our solar system together. The Earth is ripped away from the sun.
Oh my God. And it doesn't stop there, does it?
It reaches the microscopic level. The expansion of space becomes so violent it overcomes the electromagnetic force holding molecules together, then the strong nuclear force holding nuclei together. In the final fraction of a second of the universe, atoms themselves are literally shredded apart by the expanding vacuum.
Torn to subatomic shreds. Excellent.
Huh.
Well, what is the final scenario?
The big crunch. This is the ultimate fate. If dark energy is a dynamic quintessence field that eventually weakens, or if the Yonsei age bias theory is correct and the universe is already decelerating.
So gravity finally wins the tug of war.
Yes. The expansion of the universe gradually slows to a halt. For a brief cosmic moment, the universe is static. Then, the collective gravitational pull of all the dark matter and baryonic matter begins to pull everything backward. The universe starts to contract, the voids shrink, galaxy clusters merge. As the universe compresses, the ambient temperature of the cosmic microwave background skyrockets.
Wow.
The night sky becomes blindingly bright and unimaginably hot. Stars are destroyed not by burning out, but by colliding or being vaporized by the sheer ambient heat of the collapsing universe. Eventually, all matter, all energy, and space-time itself crush back into a single, infinitely dense singularity.
Which sounds remarkably like the initial conditions of the Big Bang.
Exactly. The Big Crunch naturally gives rise to theories of a cyclical universe, a big bounce, where the collapse triggers a new Big Bang, and the cosmic story begins all over again. But when we look at these apocalyptic outcomes, fire, ice, or subatomic shredding, it can evoke a sense of cosmic dread. But we must ground this in reality. Even the most aggressive Big Rip models put the end of the universe tens of billions of years in the future. The Earth, our sun, and our entire solar system will have lived out their natural life cycles and perished billions of years before dark energy writes the final chapter.
It's a deeply humbling timeline. Contemplating these endings forces us to confront the ultimate legacy of our existence. If the universe is destined for a cold, dark heat death, it makes the brief, fleeting window where stars shine and consciousness can look up at the sky feel incredibly rare and precious. It gives meaning to the fact that we are here right now, capable of asking these questions.
We are a way for the cosmos to know itself, even if it is only for a fleeting cosmic second.
Which brings our journey through the dark cosmos to a close today. But before you take off your headphones, I want to leave you with one final, lingering concept to mull over tonight when you look out your window. We've discussed dark energy as a constant vacuum pressure, a shifting scalar field, and even an illusion of miscalibrated standard candles. But there is a fringe avenue of theoretical physics that suggests dark energy isn't a thing pushing us apart at all. What if the accelerating expansion is the shadow of a higher dimensional reality bleeding into our 3D universe? What if the empty space inside the room you are sitting in right now, the microscopic gap between you and the walls, is intimately, quantumly entangled with the exact same mechanism that is ripping distant galaxy clusters apart billions of light years away? The universe is vastly stranger, more intricate, and more connected than our standard models can comprehend. Big thanks to all of you supporting GL Deep Dives. You're what keeps us alive. If you're enjoying the content, make sure to follow and subscribe so you don't miss what's coming next.